Okay, we all experienced abnormal heat during the past few days, specifically here in the Western Cape, and we really look forward to cooler temperatures over the next few days. There may be many reasons for this extreme heat, but we were warned about a week before it started. Today, we will get a better understanding of what makes it possible to get these fairly accurate predictions days in advance. Kevin Rae is the Chief Forecaster, Disaster Risk Reduction of the South African Weather Service. Kevin was originally scheduled for our meeting in October last year, but he had to withdraw due to high-level interactions with the Independent Election Commission shortly before the November elections. I also scheduled a trial run with Kevin, and once again, recent weather events forced us to change the schedule date. So you can see weather forecasting is a very current affair, and Kevin is a sought after man. If the politicians wants to know what's going to happen, they actually ask him. Kevin will explain what technology they use to analyze future weather patterns. It will make you watch weather forecasts in future from a different angle. So welcome, Kevin, eventually, and I'm looking forward to your presentation. So over to you. I've enabled the screen sharing, so you can open your presentation and just see if all of that works. And I'm going to mute everyone else.
Thank you very much. Yeah. Thank you very much for your glowing introduction. Mild extreme weather is something that we pretty much have to live with. Now, you know, the planet is heating up. Climate change and global warming are literally concepts that are discussed by everyone nowadays. You were talking about the heat wave that we had in the Western Cape. Just the week before that, we had a heat wave in Argentina. This is just my cat Mila, who's just photobombing the proceedings here. But I'm going to switch over to my presentation. If you will just bear with me for a moment. Right, super duper. Okay, here we go. So as Johan had said, I'm the chief forecaster for the South African Weather Service. Previously, we referred to ourselves as the forecasting department. However, nowadays, and in keeping with the approaches worldwide, we work very closely with disaster management structures. So consequently, we refer to ourselves as disaster risk reduction. And you will see a little later on in some of the content why we refer to ourselves as disaster risk reduction, where there's so much extreme weather going on nowadays that it's not just a matter of describing what the weather is at any point in time, but it's really, really critical for us to try and get a handle on how is that weather going to interact with the built environment, the natural environment, as well as humans out there. Just before we step off into the content, I thought that a full disk image, a satellite image of this morning would really sort of set the tone for the discussion. Some very interesting things that one can infer from this particular image. This is the Meteosat 2 geostationary satellite, and it's positioned 36,000 kilometers above the Earth, directly over the Greenwich Meridian. So the really, really cool thing, and this is not the only Earth satellite, there are many others, and we will discuss a bit more of the content later on in the presentation. But this particular satellite is owned by a European consortium called EUMETSAT, and we are just very lucky that for Africa, we are under the footprint of this particular satellite. Why is it particularly at 36,000 kilometers above the Earth? The reason is that it rotates at that particular altitude, it rotates at exactly the same speed that the Earth rotates. So it's always in exactly the same spot, and we have that convenience of being able to animate satellite images. I'm not going to do an animation right now, but we get these images across probably about 24 different channels, including infrared and also false color composites. We get them at 15-minute increments, and it's really exciting for us to be able to track the weather. As you can see in this particular image, and this was 7 o'clock local time this morning, being the Southern Hemisphere summer, our day was starting a little earlier than Western Europe, with Western Europe still being in darkness at that particular time. You could see the remnants of the tropical depression. I'll mention more about that in the next slide. And then just before we depart from this slide, a very interesting phenomenon. You don't always see it. It's a sort of a seasonal type of thing, with very calm equatorial seas just off the east coast of Africa, a phenomenon known as sun glint, where the ocean is literally acting as a giant mirror and reflecting sunlight back to the satellite. Now, here is the false color image this morning, and I thought this would just sort of, again, set the tone for our discussions later on. The remnants of this tropical system, thankfully, it's not expected to influence South Africa at all, although we are right at the beginning of the tropical cyclone season for the Southwest Indian Ocean. And that largely covers the months from January, February, March through to about April or so. And you would recall the absolute devastation that we had over Limpopo and Mpumalanga with Tropical Cyclone Eloise just about a year ago. This system, by contrast, moved in over central Mozambique. In the last 48 hours, and you may have seen on social media, evidence of tremendous devastation and flooding over southern Malawi, with dams overflowing, etc. So that's just some food for thought. We are monitoring the situation, keeping a close eye on things, but at this stage, no further systems just yet for our particular domain. Now, just a quick thought and retrospective. If we go back to the early history of forecasting, naturally a very, very strong marine and seafaring flavor, where this was an absolutely critical type of activity for the early seafarers, and I've just picked out at random the Vikings, and then if we go advance to the voyages of exploration, the Portuguese, the Spanish, the English. I should have actually included the Chinese as well back in medieval times. Very few instruments in those very early days, but a very strong theme of a careful observation of the state and sky as well as the ocean. Many rules of thumb, and a lot of these rules of thumb persist to this day. Red sky in the morning, sailor's warning, that kind of rule of thumb. And it was only really later on that observations of atmospheric pressure, wind and temperature, those started up round about the mid-1600s and through to the 1700s. But there was a lot of variety of various different instruments. You'd be familiar with the mercury barometer, which was even used in common use up until about the 1980s. So the sort of a thread that I'm going to try and develop through the course of this presentation is that at intervals, advances in telecommunications and information exchange, and even preceding the supercomputers, that advancements in telecommunications really resulted in advancements in meteorology as well. And it was only really once we had the advent of the telegraph and Morse code hand in glove with that in the 1830s and 1840s, that information could be exchanged over great distances very rapidly, and that spatial ideas of information exchange were becoming quite important. So not just what is happening at my location, but simultaneously what is happening at other locations, and how do all of those relate to weather changes. Again, just a few sort of highlights just to sort of prompt our thinking. There's the development of the radio through Marconi. You would recall the very first SMS sent by the Titanic as it was sinking. Then telex and radio telex in the mid-1900s. That was a very important thing, and I think some of you may well have worked with telex communications, and especially our subantarctic islands. That was a very important means of telecommunications prior to the internet and GPS satellites, etc. And then also a very important thing from a meteorological point of view was the so-called GTS, the so-called Global Telecommunications System, which was just really a vast web of telex communication being interchanged, and it was the World Met Organization in the years after the Second World War who largely drove that. Now, also something that I haven't really mentioned as a particular slide, but it is just very interesting that since the end of the Second World War, there's been a free and unfettered exchange of meteorological information worldwide. I remember starting as a learner technician back at Oliver Tambo. It was called Jan Smuts back in those days. And we would have to manually plot a lot of information for aviation all over Western Europe. And you had to actually be careful because the Soviet information came in with winds in meters per second, whereas the Western observations were in knots. So while there was a complete standardization of and free exchange of information, a lot of the time the units differed. But gradually we've gotten over those kind of idiosyncrasies. But it is just very interesting in this day and age of competition and jealously guarding data, that meteorological data has traditionally been exchanged very freely. And especially if one is in a very remote location, such as Antarctica, that is very, very important from a safety point of view. So I mentioned Morse code and the telegraph. Information started being exchanged from a spatial perspective. Sorry, here's the cat trying to photobomb me. She loves the keyboard. If we advance to 1875, Sir Thomas Galton was one of the first people to try his hand at a synoptic analysis. And for over 100 years, this was pretty much a standard feature in newspapers of the day, where it was the circulation of what was happening yesterday that was pretty much analyzed. But people had very little idea of what was happening from a spatial point of view for the current day or even the next day, so to speak. Now, some of the fathers of this technology, a very, very important person from our perspective, Bjerknes, Wilhelm Bjerknes, and in the early 1900s, he developed quite a number of calculus theorems. He built on the work of Lord Kelvin. Now, I'll just set your minds at rest collectively. We're not going to delve into any calculus today. I would have difficulty recalling that from my university years. But the very important thing was that the understanding was there. And if Johan shares the presentation with you, you'll be able to read through this at leisure. But the very, very important thing, and I'm just going to read part of it verbatim, is that he suggested that weather prognosis should be considered as an initial value problem of mathematical physics. In other words, you had to quantify what your situation was, and could be carried out by integrating the governing equations forward in time, starting from the observed initial state of the atmosphere. So he was one of the very, very first people that actually came to grips with this idea of gathering information, defining it from a mathematical and physics point of view, but then integrating it forward in time. And there actually was the problem, that certainly surface analyses could be done throughout the 20th century, throughout the 1900s, even up to and including the Second World War. But there was very little idea of what was happening in the upper air. This is just literally one very thin slice of the atmosphere, and it only partially describes what is going on. And again, the important thing is that Bjerknes knew the formulas, he knew how to go about it. It's just that the calculations themselves were just so staggeringly complex to calculate at various grid points over time through 3 dimensions. And it was only in the post-Second World War years, once supercomputing started to take off, that we were actually able to run these types of simulations in near real time. And now, and this is just literally advancements in the last less than 100 years. Now it is commonplace to have a 7 or 14-day outlook, and we just take this as a given. On your cell phones, you'll have a 7-day outlook for any particular spot across the world, and a 7-day forecast now is as accurate as a 48-hour forecast was a scant 40 or 50 years ago. So that's just a sort of quite an interesting perspective. I mentioned the Second World War, and just 1 or 2 aspects I would just like to touch on very briefly. That, you know, here's an example, the D-Day landings. I'm not too sure if any of you have heard of the days preceding the 6th of June. We're all familiar with the landings themselves, which occurred on the 6th of June, a temporary break in the stormy weather, the rain, which had persisted over the last 36 hours, that had temporarily lifted. The seas were still quite stormy. Unfortunately, many of the soldiers departing from the landing craft, there were a number of drownings before they even got to the beaches. But a critical thing was that both the Allies as well as the Germans in occupied France, they had meteorological information. The Germans had many observations coming in from U-boats out in the Atlantic, but it was just luckily that the Allies were able to process a lot of the information around the British Isles, and they were able to anticipate a brief easing off in the stormy conditions. And hence, they decided on the 6th of June and caught everyone by surprise. The Germans had felt it would be way too stormy for the Allies to mount such an invasion. So that was just an interesting aspect regarding how weather guidance can and still is an exceptionally important aspect during wartime. And it's been particularly during wartime that many technologies such as radar have been developed. And generally during wartime, although, you know, a war isn't you know, it's a type of thing that I think all of us try to avoid, but there is the aspect that generally technology makes great leaps forward during wartime. Just before I depart from this mention of the Second World War, another weather-related aspect, I'm sure everyone's familiar with the 2 atomic bomb blasts at Hiroshima and Nagasaki, respectively, towards the end of the Pacific theater of wartime engagement. But a lesser known aspect is that Nagasaki was only really a secondary target. The initial target for the second bombing was supposed to be the town or city of Kokura, and it was only by virtue of the fact of the presence of broken clouds and smoke detected by Enola Gay, which on the day was performing the role of a weather reconnaissance aircraft. And it was by virtue of the fact of this observation, and again, at the risk of stating the obvious, decades before the presence of weather satellites, that they decided rather to shift to the secondary target of Nagasaki. So the inhabitants of Kokura, lucky for them, but unfortunately for Hiroshima and Nagasaki, really devastating occurrences there on the 6th and 9th of August. A quick thought now, I'm sure all of you are familiar with this idea of input, processing, and output. I'm not going to dwell on it too long, but just to say that the whole process of forecasting falls very neatly in line with the whole computerized idea of gathering all your input, observations, etc., from various different sources, processing that in some shape or form, and in our particular case, trying to process that as fast as possible. Naturally, storage is a very important aspect to be able to go back to previous events and to reanalyze those. Your output, of course, going out to all your different clients, and then generally there's some kind of feedback loop in terms of what did we do well, what did we do not so well, and perhaps to investigate or pursue some kind of improvement in your processes. Now, a few very quick slides, and I'm sure many of you will be familiar with all these traditional types of meteorological information, but nowadays there's such a vast array of observations. I don't have the time for that today. Perhaps we could investigate that in a further talk. But I had mentioned the importance of measuring the atmosphere itself. As I'd said earlier on, over the last few hundred years, surface observations have been a very traditional, pervasive, ubiquitous thing. Measuring all your surface variables, but it's particularly in terms of aviation safety, and then also the correct and accurate running of numeric weather prediction models, where it's absolutely critical for us to know what is happening in the atmosphere. Now, this type of balloon, these have been launched since about the 1950s, International Geophysical Year, a hydrogen or helium-filled balloon, which will fly and lift perhaps at about 1,000 feet a minute, going right up to the edge of the troposphere, and it will generally fly for about 80 or 90 minutes, carrying in information. Nowadays, these radiosondes are literally the size of a packet of cigarettes, everything computerized. Winds are worked out by GPS. So it has a GPS transmitter on board, and this type of sounding is really tremendously important, and especially so in the Southern Hemisphere, where we don't have a lot of land mass. So those subantarctic islands with teams doing meteorological observations, and typically these types of soundings twice a day. These are really, really critical for us. This is just an example of the kind of graph that you get: wind direction and speed with altitude, temperature, and humidity. I won't dwell on that for too long. Something I would like to mention on the theme of upper air observations. Nowadays, with commercial airliners worldwide, very similar instrumentation is carried on these commercial airliners. The program is called AMDAR, or ACARS, and in flight, as these aircraft are traversing the open ocean areas, as well as on takeoff and landing, these reports are transmitted in near real time, and there are literally thousands of these flights every day and millions of pieces of information, and all of those go into the numeric models. Unfortunately, you can see in the southern hemisphere far less in the way of activity, but northern hemisphere, really, really spectacular coverage there. So just an example of the variety of weather observations. This is just an example of a flight that was on its way to landing at Miami in Florida, and a wealth of information that aviation forecasters can glean from this. But once again, of course, all of this is ingested in near real time into the numeric models, and it's so important to get that initial state of the atmosphere correct. And again, just on the theme of instrumentation and information coming in, naturally satellite information. Here's a false color image of a severe storm, all sorts of things that can be inferred from geostationary satellites. Of course, weather radar, we're all familiar with that. I won't dwell too much on that. I think I do have a slide coming up. The South African Weather Service also has a lightning detection network, obviously very important in near real time and from an aviation point of view, and also the historic data of building up a database of information there. And this information, depending on where you are in the country, can be accurate down to about between 50 to 200 meters. Very useful for us. And also from a safety point of view, a lot of this information goes out in near real time to golf courses to alert them when lightning strikes are approaching golf courses. Then, of course, your traditional surface observations, what we refer to as synoptic reports, land and sea. And as I said, in the southern hemisphere, ship reports are tremendously important, ships and islands, because there's so little land mass and the southern hemisphere is dominated by ocean. And just a quick thought, and this might perhaps be the elephant in the room. So much of our information nowadays on the surface is collected by automatic weather stations. These things are completely automated. You get a report pretty much every minute across all the traditional parameters that we wish to monitor. But these instruments can be out in really, really remote places, deserts, etc., and they will continue to work uninterrupted as long as they have power. But the point being that as recently as perhaps the 1980s, I think these stations only started being installed in the 1980s, that just the measuring of surface variables was a tremendously labor-intensive exercise. I experienced that in the 1980s, where even just to make observations of pressure, temperature, etc., you literally had to walk around and gather the information, code it manually, and then send it out via telex. So the gathering of information was extremely laborious and time-consuming. Never mind the time that you would want to devote to actually running computer models afterwards. A slide dealing with weather radar, and again, a very exciting type of technology. This was a particular severe storm supercell back in 2013, just near Irene, and this was the cross-section of the particular storm, supercell storm, and here is a corresponding photo of the same storm. Very interesting things that one can do with radar data. You can do cross sections and infer all sorts of interesting things. But once again, the limitation of this data, due to the curvature of the Earth, you can only really sense the storms with any degree of accuracy within about a 200 to 250 kilometer radius around the station. So once again, with South Africa being a very large place, it's just beyond our ability to cover every single spot in South Africa with a weather radar. By contrast, in the United States, they have much better coverage, but it's primarily because of the problem of the curvature of the Earth that one has to try and have a greater density of weather radars. We only have about 12 such systems countrywide, and consequently, we rely a lot on satellites to complement the data available. Now, just a quick few thoughts regarding processing. I'm not going to spend over much time on this. I just have an eye on my watch, and I think I've spent about 30 minutes or so. I'm close to the end of the presentation. I'll be able to finish in the next 10 minutes or so. Now, this was a very early numeric representation, mean sea level pressure, generated by the UK Met Office back in the early 60s. There were a lot of early computers in the 50s, 60s, and 70s, but it was only when we got to the 1980s and 1990s, and particularly, I think all of you sort of pretty much being my age group would recall that in the mid-1980s, we had personal computers becoming available, albeit at an eye-watering cost. But the very, very big role player in terms of large computers, the world standard was pretty much IBM. Gradually, Control Data Corporation took over, and you may have heard the name Seymour Cray. Here's an American computer engineer, really, really brilliant. Unfortunately, I think he died in a motor vehicle accident, I think in about 96 or so. But he was really, really one of the central founders of CDC. And then later on, he broke away and developed his own supercomputers. At the Weather Service, we're very proud to mention that we have one of the later iterations of the Crays. Now, literally, it looks like a couple of cupboards standing in an air-conditioned room. They look very nondescript, but tremendously powerful. You would have heard nowadays of massively parallel computing, where the computers utilize thousands and thousands of microprocessors. And the critical thing is, how are those arranged? Are they arranged in nodes or stacks, etc.? And this was something that Seymour Cray was very skilled at, taking existing technology and making it faster. So just to give you an example, and I'll explain what flops are. It's floating point calculations per second. That is essentially what a flop is. What is a T-flop? That's a teraflop, and that's essentially 10 to the 12 calculations per second. So that's a million, or mathematical billion calculations per second. So 76 teraflops. That is the capability of this particular Cray. And now that enables us to run a few local numeric models. We use the unified model developed by the UK Met Office, and a theme that is quite important for countries nowadays. We started off with so-called global models covering an entire hemisphere. Now what we do is nested regional models where we take the starting conditions from a global model and we use that as the edge of the domain, and then we run very high resolution models within that. So this is the domain for the 4-kilometer resolution, and then we even have a 1.5-kilometer resolution for just a smaller domain around Southern Africa. And generally, though, the output runs up to sort of between 48 to 60 hours ahead, but up to 72 hours in some cases. And we update that 4 times daily. So in other words, every 6 hours. Now, just a quick thought, and sort of coming back to this theme of what floating points per second are, the exponential rise of computing worldwide. Now, I think some of you would say, gosh, no, this looks linear. But look for a moment at this y-axis that one can actually see this is a log linear transform. This is actually an exponential rise in computing worldwide since the mid-90s. And I was mentioning teraflops earlier on. There are computers generally, and you will see in the list on the next slide, generally we talk about petaflops, and there are computers even approaching exaflop. And if we have a look here, this is just sort of almost a top 10 of development of recent computers, and you would see IBM, Fujitsu, Cray featuring very strongly. So it's just incredible. Anyone who wants to read up a little bit more, there's some very interesting Wikipedia pages. The link is there for anyone who's interested. Now, what are some of the exciting things that we do with supercomputing and numeric model output? Quite an interesting aspect, and this was sort of explored in the 1990s, that the scientists running numeric models realized that even if you had very minor tweaks to your control conditions, that you could end up with a whole variety of outputs. So once again, the very important idea of knowing what the initial conditions are. But this uncertainty was used to our advantage, where they realized if you fiddle with the initial conditions and there make very, very minor changes to the initial conditions, you will end up with what we call an ensemble of outputs. And the very cool thing with this is that you're able to cluster those outcomes, and you're able to start getting into probabilistic forecasts, where you could say, well, 30% of the outcomes want rain at Cape Town, and statements very much like that. Also, a recent example, Tropical Cyclone Cody, that was mid-January, that was just about a week or two back. And here we have a plume of outcomes from the initial position. And this is, again, a graphic example of how ensemble modeling approaches can help us get an idea, not just of one possible path, but a whole clustering of possible paths. And this was just indicating that Cody would most probably just slide past the northern island of New Zealand. So once again, just an illustration of the practical usefulness of ensembles. Now, my final few slides, just to give you a flavor of where forecasting is going. I think in about 2017 or so, the UK Met Office started off with what was then a fairly radical idea of what they called impact-based warnings. The German weather service, Deutsches Wetterdienst, also started off with impact-based warnings, but the UK Met Office is still the world leader, and they've assisted us quite strongly in terms of getting this going at the weather service. We operationalized this just before COVID-19 broke out. What is impact-based forecasting? The idea is that traditionally we would have threshold-based warnings, which were fairly nondescript. You'd be making a statement, something like 50 millimeters within the next 24 hours. We expect heavy rain, etc. But everyone could rightly say, and especially in the context of global warming and climate change, how will that actually impact on me on the ground? For instance, I can just use an example, the recent heat wave we had, where it's one thing to describe it meteorologically, but what does it mean to people? Heat waves are known to have the capacity to cause mortality, especially amongst newborns and toddlers, and then also the aged as well. And there's many academic articles underscoring this. So a heat wave is not just something that is of interest, and was the maximum 39 or was it 40, but there are weather phenomena that can literally kill people, and we have to try, both for the public as well as for disaster managers, we need to try and quantify what is the level of that risk, and hence the very strong emphasis on impact. This is our impact warning table, and rated in increasing numbers from 1 right through to 10. And what are we doing? We're comparing the likelihood of that particular phenomenon. Is it a very low likelihood, but will it perhaps have significant impact? We then decide on a level 4. So for the public and for disaster managers alike, the very useful thing is that you can start assessing your own particular level of exposure to this particular phenomenon. And just as an example, okay, this was a thunderstorm warning, a level 2, I think for the Free State, was it, last week? But here at the other end of the scale, and earlier in the presentation, I mentioned a tropical cyclone Eloise. Now, 23rd of January, here was a satellite image. You could see some information from our lightning detection network, positive and negative strokes overlaid over the satellite imagery. But we ramped things up and we went for a level 10 warning over the Lowveld. And that was the very first time we'd actually invoked a level 10. But by contrast, other provinces, although there was a risk of rainfall, that those other provinces were far less exposed. So once again, the graphic map literally being able to allow much more in-depth analysis and understanding. Now we've got to sort of pretty much the end of my presentation. Just before I finish with the slides, and I will really be keen to hear any questions from everyone from a meteorological perspective. But just a quick thought, there is a YouTube clip that I think Johan may well have shared with you as a group. But although meteorological observations are obviously the prime reason for geostationary satellites being up there, not just one, but two meteorological satellites captured the very, very dramatic explosion of the volcano out in the Tonga area. This was now on January the 15th. And the really spectacular explosion and spreading out of volcanic clouds, and also the shock wave that you may well have read about. This shock wave traversed the entire Earth. It even passed over South Africa. Our meteorological equipment showed a bit of a spike in pressure, and this was indeed the case worldwide. So the very, very interesting thing is that this explosion, I believe it's the largest volcanic explosion which has ever been picked up by meteorological satellites. So very important information from a volcanological and geological point of view, not just from the point of view of meteorology. So in that YouTube clip, there are some very interesting perspectives mentioned there. But I think, Johan, yeah, this is my final slide. I think many of you would be aware of the very, very dramatic change, the sort of before and after shots that afterwards this whole caldera, well, it was a caldera to start with. These are the very edges of an earlier mountain that had been blown away, and this was now secondary development that had developed over the last, I think, perhaps 100 years or thereabouts, but in a very similar way to the Krakatoa explosion of the late 1800s, that all of this was pretty much blown away. So very thought-provoking in terms of, and humbling as well, in terms of just how insignificant humans are in the context of what can potentially be thrown at us through violent occurrences on the earth. So Johan, I think that then concludes my presentation, and I think I'm going to stop sharing then.
Thank you, Kevin. That was fascinating, and I didn't realize that you all have to be mathematicians to be able to forecast weather. It looks like serious computing there. Just for the members, I do have the video that Kevin referred to, the Tonga eruption video, and the link will be, I'll give it the link to you at the end of the meeting today, that you can watch it in your own time. You're welcome to ask questions. I've got a question here, Kevin, from Bernard. He says, while temperature prediction is improving and accurate, why is the degree and amount of rainfall to be received not more accurate?
Yes. Now, could I respond to that question sort of one by one, Johan?
Yes, yeah, you can.
Would that be suitable for you? Yes. Okay, that's a very, very good question to ask, and especially in the context of numerical weather forecasting. You would think that with such fine grid networks, certainly temperature pressure, wind direction, and speed are very well captured. Something I neglected to mention is that at the same time, there's ocean forecasting, and then we also have linked models that try and track the interaction between the atmosphere and the ocean. But coming back to the question of rainfall, what is the problem or the challenge that we have with rainfall? There's a concept called parameterization, and essentially that is essentially a sort of a code word in meteorology, where we say all these other things like pressure, temperature, etc., those can be quantified explicitly using calculus. Obviously, there are little bits of error that tend to multiply and snowball as we go further ahead in time. So the general problem with mathematics and calculus, that if you are making a numeric approximation of a particular phenomenon, as you go further in time, there's more and more uncertainty, because that little bit that you're throwing away tends to snowball. So with rainfall, it's something that we can't really quantify explicitly. So then what happens, we start having to make approximations and guesses, and having to do a sort of a best guess at what the rainfall output would be. So consequently, if you're looking at tropical rainfall, there are certain parameterization schemes that approximate that rainfall, or other parts of the world we have approximations for rainfall as well. So rainfall isn't the only meteorological parameter that is difficult to quantify, but it comes back to the idea that from a mathematical point of view, it's very difficult to calculate, and the rainfall output is then at best an estimation. You have something that is known as QPF, quantitative precipitation forecasts. Sometimes they're good, sometimes less good. And that's why, and again, at the risk of obvious, people have said to me, perhaps since the 1980s, are we as meteorologists not concerned that we're going to lose our jobs, that artificial intelligence will take over completely? Certainly, there are certain mundane parts to our job, like developing weather maps 14 days ahead. The computer models do that fantastically, but there is still, at the current time, and I would venture to suggest in the future times, that the role of a forecaster is one of interpretation. If I'm dealing with you as a client, perhaps you have a concern that your tomatoes might frost tomorrow morning. Or are you perhaps a commercial airliner pilot and you have other concerns regarding wind shear, etc. So my role will always be one of interpretation. But just to close that answer, nowadays there are satellites. The so-called TRMM satellite is one of them. Tropical monitoring, the acronym is TRMM. You could Google that. And it's we try and quantify what is happening right now in terms of rainfall, in terms of remote sensing. And if we compare that to what the models are doing at the moment, we get an idea of, are they performing well? Are they performing less well? Do we want to tweak that output a little bit to bring it in line with observations? So that is essentially the answer. I might have gone off at a bit of a tangent, Bernard, but some parameters we can do better than others.
Good. Next question, Angela asks, is long-term historical data used to predict potential changes in weather patterns over the next 10 or 20 years?
And the question was from?
Angela.
From Angela. Angela, again, a very good question. And it's yes, for a number of different reasons. In the good old days, before supercomputing, forecasters used a lot of rules of thumb. There was a very strong emphasis on generating these wonderful works of art with isobaric analysis, etc. And they would generally use a 30-year history of what has happened, say for South Africa or the UK or New Zealand. They would use a 30-year history of what has happened, and those extremes of rainfall, temperature, etc., were pretty much the gold standard. However, as you would all be aware, with the Earth being a hotter place and concepts like climate change and global warming becoming something we're talking about right now, all that has literally been thrown out the window. A lot of the time, forecasters don't know anymore what is the most extreme 1 hour rainfall that George could experience in December or something like that. So we're living in very, very changing times. And it's very unsettling for a scientist because you don't have the luxury of being able to draw on that history as strongly as you used to in the past. So thanks very much for that. A very insightful question.
Kevin, final question, and it's very related to this previous one, and also I think a very South African question, and it's coming from Jeff. Jeff says, we hear of places that are regularly flooded in rainy seasons, often involving extensive damage to people's homes. Do city planners and developers access long-term weather data before an area is developed for housing?
Yes, Jeff, again, a very good question. And it gets me onto a very topical aspect of forecasting. I was mentioning that perhaps in the early days of my career, up to about the 1980s or 1990s, we had a very sort of scientific dismissive view of things. We would generate a particular forecast, and then we would say, well, the forecast and the warnings are out there. It's up to the hydrologists or the city planners or disaster management to deal with it. And we would sort of do a kind of a Pontius Pilate and wash our hands of it. Nowadays, we don't have that luxury, and we deal very, very closely with disaster management. I can just mention that I sit on a particular committee called the National Joint Drought and Floods Coordination Committee. It's a very, very long acronym. But the interesting thing there is that when we get to do presentations and we say, gosh, guys, Limpopo, there's a lot of rain coming up in the next week. Please, if you can get out there, ask the municipal folk to clean the drains, clean the debris from under the bridges, etc. And it's a recurring theme that we have, especially in this country where we have to deal with sudden downpours from rain. Again, not an analogy, but I can just compare a similar type of occurrence happening. If we think of the UK, with large parts of the UK being heavily modified, you've got roads, built up areas, etc. Little streams which perhaps in the 1960s could deal with overland runoff and had sufficient capacity. Now you have, in the UK as well as here, great transformation of the urban environment, large areas that are tarred, shopping malls, parking lots, etc., with much more overland runoff. And then the interesting thing in the UK, a phenomenon that we've seen is that the type of rainfall is starting to change from the kind of light set in, soaking in kind of rainfall to more in the way of thunderstorms and heavy downpours. And many of the flooding events you've seen in the UK have actually been triggered by deep convection and thunderstorms that they're not really used to, and that their urban environment isn't really geared to cope with that. And just before I depart from that particular theme, even in my own lifetime, I grew up in the Centurion area just outside Pretoria, and we can remember in the early parts of our career that you would need perhaps 50, 60 millimeters of rain to cause a flooding event along the Henops River. Nowadays, by virtue of the fact of all this urbanization and dramatic overland runoff, there's very little infiltration into the ground. That has reduced to something like, perhaps a third of that, maybe about 20 or 25 mils will actually give you flooding on along the Henops. So even in my own lifetime and in your lifetimes, I think we're all experiencing a change to the environment we're living in, and many of these are weather driven. Thank you.
Rudolph, I saw you've got your hand up there. Just if you've got a question, just unmute yourself.
Okay, thank you. Just one question, one information. I'm actually running an automatic weather station on my roof, and the information is also in the internet. So if someone is interested, how hot is it on my roof at the moment? It's 27.2 degrees and 16.6 south-southeasterly wind. It's actually a system I imported from Miami, also from Florida. It's called Tempest, and it's very useful here. And if somebody is interested, just has to call me or send me an email or something, or maybe via Johan. And my question is, and that's also based on the accuracy of rain prediction, is there actually a weather radar in the Western Cape? Because I know that from Switzerland, we have 4 radars in Switzerland, and we have a weather, also a rain forecast within minutes accuracy. Is there one here in the Western Cape?
Okay, if I could reply to that, Rudolph, I'm going to split my answer into 2 parts. Firstly, I'm very, very encouraged to hear that you are doing your own weather observations at your place of residence. Something that I can mention just as an anecdote, a childhood friend of mine, Professor Willem Landman, he's currently a professor of meteorology at Pretoria University. And I remember from his school days even, where he was very fastidious with keeping weather records, and he was even able to start tracking changes just at his own place of residence. So it's just an example of you know, even if you start off small, as long as you maintain a long period of observation, that those observations do become increasingly valuable. To come to the weather radar aspect, it's not altogether good news for the Western Cape. The awkward thing is that because of the mountains in and around the Western Cape, and particularly within fairly close proximity to Cape Town International, the mountains themselves form a significant barrier to weather radar energy. So you have one of 2 choices. You can put up your radar at the airfield, as indeed they have. They have aviation radars there. We decided to put a radar on top of one of the mountains to rather have a wider sweep of the area. Also something that we also invested in, but they're not operational at the moment. The idea was that we invested in 2 mobile X-band radars specifically to use in and around the Western Cape. But unfortunately, those radars aren't operational at the current time. So it's sort of good news and bad news. But a big challenge that we have, and the same holds for our coverage of the Kruger Park and the Mpumalanga escarpment. The escarpment is such a massive topographic barrier to radar energy that it's unfortunate to have to use a weather radar. We've got one at Skakuza, but its sweep is very limited because in the west, it can't go any further than the topography of the escarpment. But that's a very good question, and thank you very much, Rudolf, and I really encourage you to continue with your observations very much in the vein of Professor Landman.
Thank you, Kevin. Just a final question from my side. I mean, we all have some or other internet or computer program or app on our phones to get the latest weather news. Now, one of the popular ones is YR, but in my view, it's not always that accurate, and maybe because it's coming from the Northern Hemisphere. Now, which one will you recommend to be the most accurate for weather forecasting for a personal use on a cell phone or smartphone? What app would you recommend?
Johan, the short answer is that we have an app that was developed in collaboration with AfriGIS. It is the Weather Smart app. That's one word, Weather Smart. And it's absolutely free. You can get it at the App Store, and you can, I think, up to 5 different localities across South Africa. You can get a whole 7-day forecast. And if there is radar information available, if you do a swipe up vertically, it will bring up your local radar coverage as well. The information has been dumbed down, and I use that word in inverted commas, particularly, and I'm talking about the radar information, because we have a concern that third parties would take our radar information and use it for commercial purposes. But the exciting thing with the radar information is that we've applied the Titan storm tracking algorithm to it, and you can see not just where the storms are at the moment, but where they're going to move in 30 minutes or 60 minutes. It's more useful for the eastern half of the country and much less so for the Western Cape. But it's very intensively used, even by pilots, might I add, for the eastern half of the country. So once again, it's been developed in collaboration with AfriGIS, and the app is called the Weather Smart app, and that's endorsed by the Weather Service. Coming back to global models, and all of us, I'm sure, use yr.no and all sorts of other sources of information. All of us use them for their convenience, but it comes back to how detailed is the idea of that model. Say, for instance, you're using a global model for the entire Southern Hemisphere. Yes, it might give you information for Cape Town, PE, Durban. Generally, the coastal stations are well handled by global models. The problem comes in when you go up to places like Bloemfontein, Johannesburg, etc., at a higher altitude. Those global models only have a very primitive idea of what the topography is. At best, those global models see the topography as a whole lot of cubic building blocks over the country. So for coastal areas, I'd say use yr.no, ECMF, etc., GFS, your model of choice. Once again, the cat is photobombing me here. Coastal stations are generally far more robust. So once again, Cape Town, PE, Buenos Aires, Perth, Melbourne, all of those areas are coastal. but for a much more accurate idea of what is happening in your own backyard and for your own city, please use the WeatherSmart app.
Thank you, Kevin. Thank you. It was really interesting, and I can see everyone is really fascinated to listen to you. We can listen for a long time, but thank you very much for your time and efforts to prepare the presentation and for the presentation itself. I think we can all give Kevin at least a hand.
Right. Thank you very much, one and all. Much appreciated. And thank you for your patience as well. Thanks. I hope it wasn't too long.
No, thank you. Kevin, you're welcome to leave the meeting now. I'm just going to finish off with a few other admin issues, but you're welcome to either stay or go. Thank you very much.
Okay. Now, thank you very much, Johan. I have a Teams meeting coming up shortly that I need to prepare for. So thank you once again, one and all. Rudolph, do continue with those observations and use the WeatherSmart app, and do have a good day and keep safe. Thank you. Bye-bye.